Assalamu alaikum and welcome to the presentation. Today I'm going to do a presentation on the topic Unbounded Knapsack. Well, let us begin with the first question, and that is, what is a knapsack problem? So the knapsack problem is a problem in combinatorial optimization. So we can get the answer from this last two words, combinatorial optimization. So you'll be given with a problem and you have to solve the problem or optimize by using a combination method. So we can see over here, given a set of items, each with a weight and a value, determine the number of each item to include in a collection so that the total weight is less than or equal to a given limit and the total value is as large as possible. So from this definition, it is very hard to actually understand what is exactly happening. So I'm going to be simplifying as much as I can. So first of all, physically speaking, what is a knapsack? So knapsack is basically a bag. So you've been given a bag. So with the bag, you will also be given with items. So we can see here given items with weight and value. So you will be given items which will have a weight and a value. The goal is to fill the bag to its maximum capacity with the given items, of course, and the input obviously are given items with weight and value. So how to fill the knapsack? So here's an exemplary problem. Let us assume there are some weights W1, W2. We have taken the weights already over here. Let us assume we have been given three items, each having weight 3, 2, and 4. And the value of each three item is 8, 5, and 9. So for the item which is having weight 3, it has a value of 8, which has a weight of 2, it has a value of 5, and which has a weight of 4, it has a value of 9. And the limit, obviously there will be a limit of the bag up to which you can carry, and for this problem the limit of the bag is 7. So how do we fill up the bag in the most efficient way, in the most possible way to get the maximum value? So we can see, let us begin by taking the first two, for example. So we take the first two items, so the weight of the first two items adds up to 3 plus 2, 5, which is obviously less than 7, so we can put these two items inside the bag. So we have to now calculate the value that we are getting for these two items. So for these two items we get 8 plus 5, which is 13. So if we put the first two items inside the bag, we get the value 13. So now let us take a look in the what are the other ways we can fill up the bag. So if we take the second two, like 4 and 2, so it adds up to 4 plus 2, 8, which obviously exceeds the limit of the bag, so we cannot put these two inside the bag. So what is another option? The another option is putting this first item and the last item. So 3 plus 4, the weight adds up to 7, so we can put it in the bag. So and the value comes 8 plus 9, which is 17. So for the first instance, what we did was we put these two, so the value became 8 plus 5, 13. But for the later one, we see that for 3 and 4, we get the value 17, which is obviously larger. So the best or the actual answer will be to put these two items inside the bag, and we get the best answer. So there's a note here. We can see how to fill the bag is defined by the knapsack type. Well, I'm going to discuss about that as well, about the classification of knapsack problems. So basically there are three types of knapsack problem, that is 0 or 1, bounded, and unbounded. And there is also another type which is called fractional or integer. I'm going to give a brief explanation on each of the types. So what we can see from here is that for the 0 and 1 knapsack problems, we can either take or not take an item, much like the binary. 1 means true and 0 means false. That's from where the name came from. For each instance of an item. So imagine you have been given with a bag and you have been given with like 3 or 4 items. So what you can do is, for each item you can either take it or leave it. Once you have decided to take the item or leave the item, you cannot change that decision. It is final. So you either take an item or not take an item, and that is how you make the combination in such a way so that you get the most efficient answer. For the bounded one, what you do is you take or leave an item and change the instance of each item freely up to the bounded limit. So with the bounded knapsack problem, you can be given with limit at up to how much you can either take or leave each item. So maybe you have been given a limit of 3, so you can change your decision for each items up to 3 times, but not more than 3 times. So you can take it and leave it, then again take it, so you have already decided 3 times for one item. So that is the maximum time you can change your decision for each item. And for the unbounded part, there is no limit. You can change the instant of each item freely as many times as wanted or required. And the later two, which we saw earlier, the fractional and integer, from the words you can understand very much. That is, for the fractional part, what you can do is that if you have been given with an item, you can fraction it and take a portion of the fraction into your knapsack. But for the integer problems, you cannot do that. You cannot just divide your item or fraction it. You have to take the entire item or the whole item into your knapsack. You either take it or leave it. So here has been given another unbounded knapsack problem. So let us see the question. Given a knapsack weight W and a set of n items with a certain value val I and weight WTI, we need to calculate the maximum amount that could make up this quantity exactly. This is different from classical knapsack problem, because here we are allowed to use unlimited number of instances for an item. As I told you earlier, for unbounded knapsack problem, you can take or leave an item as many times as you can to obviously fulfill the requirement of the knapsack, because there will be obviously a limit of the knapsack. So here's the solution. So let us assume that the knapsack has a weight limit of 100, and let us assume you have been given with 2 items, one with a value of 1 and another one with a value of 30, and which has a value of 1 has a weight of 1, and which has a value of 30 has a weight of 50. And the output should be obviously maximized or up to the limit of the weight of the knapsack. So obviously it must be at least 100, or not at least 100, maximum 100. So there are many ways to fill the knapsack. So let us look at the first method. The first method says that 2 instances of 50 unit weight item. So since your weight limit is 100, so you can take 2 of these. So 2 into 50, obviously 100, so you can take 2 of the second item. So if you take the 2 of second item, for the second item you can see the value is 30. So if you take 2 of 50, the total value comes to 2 into 30, 60. Okay, let us look at the second one. 100 instances of 1 unit weight item. So for 1 unit weight item, you get the value 1. So if you take 100 of 1 unit weight item, which fulfills the bag, you get 100 value. 100 into 1, 100 value. And for the third method, 1 instance of 50 unit weight item and 50 instances of 1 unit weight item. So you take 1 of these and 50 of these. So 50 plus 50 into 1, total 100. So for the third method, you get the total value of, for 50 you get 30, and for 50 of these you get 50. So 50 plus 30, 70. So what you can see over here is that for the first method, we are getting a value of 60 because we are taking 2 of these. So that means 2 of these. And for the second instance, you're getting the value 100 because you're taking 100 of these. So the value becomes 100. And for the third one, you get 1 of these and 50 of these. So 30 plus 50, 70. So 60, 100 and 70. So obviously we get the maximum value from the second method. So that is the actual answer for this problem. So this is basically a simple solution of an unbounded knapsack problem, and I hope this had helped a lot to understand actually what an unbounded knapsack problem can be. So thank you for your patience hearing.